Hello viewers, today discussion is on dimensions. By definition, dimension is defined as an approach in physics that relates the physical quantities of mass, length and time to ensure consistency in units. That definition tells us that when you are dealing with dimension, emphasis is on the quantities, mass, length and time. That implies that whatever quantity you're asked in any examination to find a dimension, that quantity must be transformed in such a way that the component or the formula or the constituent of that formula of that physical quantity that is given is completely made up of dimension, made up of mass, length and time. Again, that definition tells you dimension is very important because it will help you to know if units are consistent. For example, through dimension, you'll be able to say whether the unit of velocity is meter per second. From dimension, you can establish that the unit of acceleration is meter per second square, or the unit of force is in Newton. So it means that dimension has application in ensuring the consistency in units. Subsequently, I'll be telling you the importance of dimensions. But at the moment, I want you to understand clearly that the definition of dimension is based on mass, length, and time. Now, mass, length, and time are notably examples of fundamental quantities. You know, we have about 7 fundamental quantities, but we emphasis is only on these three, the mass, length, and time. Again, we will have to remember that mass has its unit in kilogram. Mass has its unit in kilogram. At this point, we'll be looking at the dimension of mass as well. The dimension of mass is capital M. Very important. So here I'll be looking at a table. This table is let's look at a table that will summarize this is a table of mass, length and time. Here we have, this is the quantity. Here let's have here the mass, the units, and here let here be the dimension. If you recall, there are two types of physical quantities: the fundamental quantities and the derived quantities. The fundamental quantities we define fundamental quantities as those quantities whose units cannot be expressed in terms of other quantities. And basically we have their unit. For instance, for this tray, the unit of mass is kilogram, the unit of length is meter, the unit of time is in seconds. Although it can be second, we can also have the unit of second in minutes and hour. Now, this minutes and hour refers to the Gaussian unit of time. Then meters is the SI unit of length, second is the SI unit of time, kilogram is the SI unit of mass. But mass also has other unit gram, the mass in gram, that is the Gaussian unit of what mass. The unit of centimeter is the Gaussian unit of length. While minute and hour refers to the Gaussian unit of time. But today's class discussion, we are not interested in the unit of these quantities. Rather, we are interested in the dimensions of these quantities. So what we need to now know is that the dimension of mass is given as capital M. The dimension of length is always taken as capital L. And the dimension of time is taken as capital T. So you need to know that the dimension of mass, length and time is given as this. So knowing this, it will help you. Any quantity given to you in any examination that you should find the dimension, you must remember this. Once you can remember that mass is capital M, length is capital L, and T is capital T, then you will have no problem with dimension analysis. So we will quickly take examples. Our examples will be focused on quantities that are derived. quantity, derived quantities. Knowing too well that for these are the fundamental quantities. So every other examples will be what? Derived quantities. So we want to quickly identify a number of quantities that, and then the question that will follow is how to get the dimensions of those quantities. For mass, length, and time, the dimensions are not derivable. They are not derivable. Simply because mass starts with letter M, so we identify the dimension to be of capital M. But for other quantities, what you do is you must derive their dimensions. Let's quickly take examples. Velocity, for instance, velocity, it is always designated with letter V. So, velocity, we want to know the dimension of velocity. If you want to get the dimension of velocity, then you have to remember the formula of velocity. Now, velocity is defined as distance all over what? Displacement all over what? Time. Velocity is defined as displacement all over what? The time. Now, if you have remembered this formula, then the next thing is to say dimension. We want to now know the dimension of what? Velocity. The dimension of velocity will therefore be equal to, you follow the formula. The formula says displacement all over time. Here, it is important you know that displacement is treated, this D is treated as a fundamental quantity, length, because displacement and length have the same unit. So you treat it as such. So if we are to obey or follow this formula, the dimension of velocity therefore will be what? Capital L all over capital T. And that is equal to LT minus 1. So that becomes the dimension of velocity. You can see for these quantities, we'll be deriving their dimensions. But for mass, length, and time, we cannot derive their dimensions. Just note that their dimensions are as I've given before. So, but for the rest of the quantities, their dimensions can be derived, and that's what we are doing. Now, for velocity, I have explained. Let's take another one: acceleration. Acceleration, of course, represented with letter A. Now, if you're asked the dimension of acceleration, it means you have to remember the formula of acceleration. And acceleration is equal to velocity all over what? The time. Now, having remembered the formula velocity all over time, the next thing you need to do is to ask yourself, is this what makes acceleration what? V and T. Now, you see that T is among mass, length, and time. Remember that dimensions, everything must be expressed in terms of mass, length, and time. Now, we do not have problem with the T because the T is a member, is part of the mass, length, and time. But the V here, we have a problem because V is not part of the mass, length, and time. What this means is that we have to substitute the velocity. We have to substitute the velocity because we want to ensure that everything that makes up acceleration are between or among mass, length, and time. And so this is equal to d all over t, which of course that represents velocity, now divided by what? The t, where this t of course is the denominator t. And we further simplify this, you know that this will be equal to d all over t times 1 all over what? T. And that will give us d all over t squared. And d all over t squared now tells us that everything that makes up acceleration are all fundamental. Where here d is displacement, and then displacement, like I told you, is the same as length in this context. Then this is what? The time. And so dimension now, we want to now look for the dimension. The dimension of acceleration, therefore, will become, we follow this formula, the dimension of d, that is capital L, all over the dimension of t, that is capital T. And because the t is raised to power 2, the dimension must also be raised to power 2. Hence, the dimension will become LT minus 2. So, you can see we have derived the dimension of acceleration. Very, very important. Let's take another example. Let's take another example. Now, let's take the dimension of force. Force. Again, you need to know the formula of force. You need to know or remember the formula of force. Now, force is defined as the product of mass and its acceleration. The product of the mass of a body and its acceleration. And so ma is what force. Now, m is mass. We are okay with this one, but the problem is the a must be removed. We have to replace a with its own formula, and so this will be equal to mv all over t, where v all over t represents what? A. But again, we have introduced v, where v is not among mass, length and time, because I told you everything must be among what? Mass, length and time. And so we will further simplify this. This will now be what? M d all over t squared. We have explained that earlier, that acceleration can also be expressed as d all over t squared. Now, with this, you see that everything that makes up force, this is the formula, therefore, the formula of what? Force. Just like this is the formula of force. So you can see that at this point, at this stage, everything that makes up force are all fundamental. Look at this is mass, this is displacement, and this is what? Time. So we can now say dimension. We now look for the dimension. In this case, the dimension of mass is capital M. The dimension of what? D is capital L. All over. This division sign is this division sign. The dimension of T is capital what? T. And because this T is raised to power 2, this capital T has to be raised to power 2. We now have M L T minus 2 as the dimension of what? The force. So let's take more examples. Now that's the dimension of what? Force. Let's take the dimension of work done. Work done. For you to get the dimension of work done, you need to remember the formula of work done. Formula of work done is equal to force times what? Distance. Force times distance. Again, you're supposed to simplify the force. If you're simplifying the force, this has to be equal to ma times what? D. Ma, where ma represent what? The force. And so if you again further simplify this will give you m d all over t squared times what? D. Now remember that d all over t squared represents what? Acceleration. And this will be equal to m d squared all over what? T squared. Now at this point, we now ask ourselves, are everything that make up work done all fundamental? Of course, that is correct. Look at m is the mass. D is the length or the displacement, and then T here is what? The time. So I've always emphasized that everything must be among the mass, length and time. And so at this point, I will now say dimension. I will look for the dimension of work done. Work done dimension will therefore be equal to the dimension of mass, which is what? Capital M. The dimension of D, capital L. Because the D is raised to power 2, this L has to be raised to power 2. All over. This division sign, of course, is this division sign. Then this T has to be capital T. Because this T is raised to power 2, this capital T has to be raised to power 2. And then you now have the dimension as M L raised to power 2 T minus 2. That's the dimension of what? Work done. Now, please again, at this point, I want to I will request my viewers to check also for the video I have made on physical quantities. There I explain how quantities, the unit of quantities can be derived. Just like the unit of dimension of these quantities are derivable. If you check that video, you have understanding. The discussion is similar to this. The only difference is that here we are deriving dimensions, but in that video we're deriving units. Very important class as well. So you can see, and in that class, we emphasize the fact that work done, energy, and movement have the same unit. And that will apply here. The dimension of work done likely going to be the same as the dimension of energy, and it will be the same as the dimension of moment. The reason is that all of these have the same unit, and so the dimension will also be what? The same. So now this is work done. Let's take more examples. Now you see moment, the dimension of movement. So if you're asked to find the dimension of movement, again, what is the definition of movement? Movement is also called torque, and the formula is force times distance. So I will not explain that because that is similar to what I've done for work done, which is why I said the movement, work done, and energy, they will have the same word dimensions. Please take note. So I won't explain that again. Just know that this explanation for work done is true for what? Moment. Now let's take up momentum. Momentum. If we are looking for dimension of momentum, the question now at this point is, what is the formula of momentum? Momentum is defined as the product of mass of a body and its velocity. Mass and velocity is simply equal to what? Momentum. Mass and velocity is equal to momentum. Now again, mass, there is no problem with mass, but we have to substitute what? Velocity. If we are substituting velocity, this will be equal to m, where velocity is displacement all over what? Time. Now dimensionally, remember that this is simply the formula. So in terms of dimension, we will now say, what is the dimension of mass? Of course, that has to be capital L. What is the dimension of D? Capital L. What is the dimension of what? T? Capital T. Of course, what we have always done is to follow the formula. And so this will now be equal to m L T minus 1. That becomes the dimension of what? Momentum. How about impulse? Dimension of impulse. Again, you need to remember the formula of impulse. Impulse is equal to the product of force times time. Impulse. Force times time. This impulse, the dimension, the unit of impulse, the dimension of impulse the dimension of impulse and unit of impulse and that of momentum must be the same. You will see it. Though the formula is different. Look at F, the force times time, but here is mass times velocity. But at the end, you will see that the formula will be the same. Let's see. Now this is equal to m times, of course, ma all over what? T. Force times time, where ma represents the formula of what? Force, and then the t. And then you further simplify this. This will give us m d all over what? T square times what? This t. And if you further, of course, this t will cancel 1, and 1 will go all out here, and this will become md all over what? T. If you now say dimension, if you look for the dimension at this point, the dimension of mass will be capital M, the dimension of D will be capital L, all over the dimension of T, that will be capital T. And that will be what? M L T minus 1. You see that is the same as the dimension of what? Momentum. That's why I said the dimension of impulse and that of momentum, the same. The units are also what? The same. The unit that is the same is in terms of the kilogram meter second system. Please take note of this. So if you are looking at the unit of momentum and the unit of impulse, in terms of the kilogram meter second system, it is the same. They are both the same. The same way the dimensions of momentum and the dimension of impulse are both what? The same. Now, that is for that. Now I'll also request that you look for, as an assignment, the dimension of viscosity. The dimension of viscosity. Now let's try the dimension of power. Power. What is power? Power is defined as the force all over what? Area. Power, the formula of power is F all over A. And so this will be equal to mass times acceleration. Of course, mass times acceleration represent what? The formula of what? Force. Then all over the length times breadth. Where length times breadth represent what? The formula of what? Area. And now this will be equal to mass times acceleration is d all over t squared. Of course, this divided by what? Length times breadth. And this is equal to md all over t squared times, if you introduce a multiplication sign here, you're going to remove the division sign. In doing that, this is all over 1. So you will have 1 all over length times breadth. So at this point, everything that makes up power are all fundamental. We'll now say dimensionally. Dimension now, we are looking at the dimension of power. Power, the dimension of power at this point becomes the dimension of mass. This small letter m represents what? The mass. So at this point, when we are looking at the dimension, we will look at the capital word M. Then this D is capital L. All over the dimension of time. That time will be capital T. And this T is raised to power 2. So this capital T has to be raised to power 2. Then times 1 all over the dimension of the small letter L here, which of course is the length, is capital L. The dimension of the breadth is capital L. So you can see that this L can cancel out this L. This L will cancel. So we will have P equal to capital M all over T square, capital T square, now times 1 all over capital L. We have again one L left here. One of the L's are eliminated at this point. So this will automatically be equal to capital M T minus 2 L minus 1. So this becomes the dimension of what? Power. The dimension of power therefore is capital M, capital T minus 2, and then capital L minus 1. So that becomes the dimension of what? Power. So now we will take more example. The dimension of stress, the dimension of strain. I would like my viewers to look at those dimensions, and then if you have any trouble, any problem with that, any problem, please on the comment section you can always drop your comment. I will respond. The method of dimension analysis. The method of dimension analysis is important because this is what will help you to solve problems that leads to equation, because we can actually use dimension analysis to solve an equation where you may have to find the value of x, y, and z that are unknown within an equation. So the following are the rules that must be observed when you're handling such cases. Number 1, please take note. If you have a pen and a paper, please write this down. Number 1 is that all numbers are dimensionless. What that means is that all numbers, they don't have dimensions. Now dimensions at the left hand side of an equation must be equal to dimension at the right hand side of an equation. Again, number 3, all constants are dimensionless. What that means is that anytime you have a constant, know that that constant does not have a dimension. Anytime you have a number, that number doesn't have numbers, do not have dimensions. Take note. Now the next point, dimensions at the left hand side of an equation must be equal to dimension at the right hand side of that equation. That's the next, please take note of that. The next again, when physical quantities are raised to a power, their dimensions must be raised to that same power. What that means is that if a physical quantity is raised to a power, the dimension of that quantity must also be raised to that same power. For example, you're told that V is raised to power X. What this means is that the dimension, this V is a physical quantity. Now, it will come to a point where you will have to solve by replacing the V with its dimension. And when you do so, the dimension must also be raised to power x. Remember that the dimension of velocity is lt minus 1. So if the velocity has a dimension x, then the dimension must equally be raised to power x. That's why I said when physical quantities are raised to any power or they are multiplied, their dimensions must be treated the same way. Let's take an example now to bring home, to make you understand all this that I have said. Take down the question, please. Take down the question. Prove, the question is, prove that the period of a simple pendulum is equal to 2 pi the square root of L all over G. Prove or show. Show that, the question is, show that the period of a simple pendulum, show that the period of a simple pendulum t is given as t equal to 2 pi the square root of n all over g. Given that t is directly proportional to L raised to power x and G raised to power minus y, where t is equal to the period of a simple pendulum. The period of a simple pendulum. The length L represents the length, and then the G is acceleration due to gravity. Acceleration due to gravity. Now, please, I want you to know, my viewers, that this is one of the application of dimension analysis, because dimensional analysis has application. One of which is it can be used to derive formulas. It can be used to prove formulas. I can see this question has to do with proving that the period of a simple pendulum is equal to 2 pi the square root of L all over G. They've given us that t is directly proportional to L raised to power x, G raised to power minus y. And they went further to tell us what t represents, what L represents, and what G represents. So I want you to know that this is one of the application of dimensional analysis. The other application of our dimensional analysis is that apart from the fact that you can use dimension to derive a formula, you can also use it to confirm the consistency or the correctness of what a formula. So let's react to the question. The question says we should explain or show or derive the formula of the period of a simple pendulum, which is usually t equal to 2 pi the square root of L all over G. Now, I told you earlier that one important or usefulness of dimensional analysis is that it can be used to derive a formula or an expression. And this is one of its application, this particular question. Now, the question said we should derive this formula, and at the same time, we were given that the period of a simple pendulum is directly proportional to L raised to power x, G raised to power y. So we're given this, from which they expect us to get this. So what we need to do at this point is to remember that in mathematics or in science, anytime we have the sign of proportionality, we have to remove it. And while removing it, this t, we have to introduce an equality sign and then a constant. Then L raised to power x and G raised to power y. Now, we would now say dimensionally. Dimensionally here means that we want to look for the dimension of each of these quantities that make up this formula. Now you know that this is a constant. It doesn't have dimension from what I've given you earlier. But t is a period, of course. Period refers to time. And so I told you earlier that time has a dimension capital T. Now L has a dimension capital L. Now the next is what? The G. The G is, we were told that G is acceleration due to gravity. And in this context, we will treat acceleration due to gravity as the same as linear acceleration, because they both have the same unit, though they differ in what? Directions. So G, which is acceleration due to gravity, is equal to d all over t squared, and the dimension will be capital L, capital T minus 2. So having known the dimensions of these quantities, the next thing we're going to do is to have them substituted in the original equation. Therefore, I will say substituting the dimensions in t equal to k l g y. So the dimensions we've gotten, we have to substitute them in this formula. Now, at this point, we will now say, what is the dimension of t? Here is capital T. What is the dimension of k? K is dimensionless because it is a constant. Then the dimension of the L here is capital L. And because this L is raised to power x, the dimension must equally be raised to power what? X. Now G is LT minus 2. That is the dimension. And because the G is raised to power Y, the dimensions must equally be raised to power Y. Now we say this is equal to T equal to L raised to power X. Of course, we will expand the bracket. What that means is that the content of the bracket will multiply what is outside. And so there is an invisible one here. That one multiplying the Y outside, that will give us L raised to power Y, 1 times Y. Then T minus 2 times Y here will be minus 2Y. Now at this point, remember we said again that dimension at the left-hand side of an equation must be equal to dimension at the right-hand side. We will soon apply that law or that rule. Now, but again, you see there is L raised to power X, there is L raised to power Y. It's possible for us to bring them together. But how do we do that? We will remember or recall the first law of indices. The first law of indices that says that if two indices are separated by a multiplication sign, what you do is you will take one. So we're going to say capital T, which of course is the dimension at the left-hand side, is equal to L. We take only one of the L's, and then the powers are added together. So this will be X plus Y, and then T minus 2Y. Now, at this point, we will recall, I told you earlier that dimension at the left-hand side of an equation must be equal to dimension at the right-hand side of that same equation. So what that means is that T at the left-hand side, look at this equation now from here. We have a capital T at the left-hand side. So I will say capital T at the left-hand side is equal to capital T at the right-hand side, which is raised to power minus 2Y. Because we said dimensions at the left-hand side must be equal to dimension at the right-hand side of an equation. So this dimension, which is capital T at the left-hand side, is equal to capital T at the right-hand side. Now, when you have done this, this now takes you to indicinal equation. In indicinal equation, apply indicinal equation. In this equation, the law says if you have a base raised to power n, for example, and is equal to another base of the same type raised to power n, because these two bases are the same and they are found at both sides of the equation, this base can cancel this, while the powers can now be what? Equated. That is indicinal equation. So we apply that indicinal law to this. So what that means is that, of course, this t is raised to power 1. This t can now cancel this t. The reason is that this is a base and it's the same as this. Applying that law, this will cancel. What we have left will be the power of this equal to the power of the other t. And if you make y the subject of the formula, y will be equal to minus 1 all over 2. You can see we've gotten the value of what y. Again, if you apply that same law, method of dimension analysis that says dimension at the left-hand side of an equation must be equal to dimension at the right-hand side, then you will now go back to this equation. You see that at the right-hand side of this equation we have L, but at the left-hand side there is no L there. But I want you to understand that there is L there, but that L is raised to power 1, 0. So if I come here and introduce L raised to power 0, you can see that I have not changed it from 1 to t, because L raised to power 0 is 1. 1 times this t will remain 1 t. So I will think of what to introduce at the left-hand side. I will think of an L. I have to introduce L at the left-hand side, because if the rule or the law says dimension at the left-hand side must be equal to dimension at the right-hand side, it means that there is L at the left-hand side. So I have to introduce L at the left-hand side. But if I'm introducing L at the left-hand side, that L must have a power that at the end it will turn into 1, such that it will not change what was given or what we already had. We had only t at the left-hand side. So if I put L raised to power 1 here, it will change it from what? Only t. We're going to be having LT. If I put L raised to power 2, it will equally change. But if I put L raised to power 0, it will be L raised to power 0 in mathematics is 1. And 1 times t remains t. That means introducing L raised to power 0, you have not changed the entire equation. And so at this point, I will now say L raised to power 0 at the left-hand side is equal to L raised to power x plus y at the right-hand side. Again, this L will cancel this. We'll have 0 equal to x plus y. Of course, this will be equal to x minus y, when y being transferred to the other side of the equation, the sign, of course, has to change. And so we're going to have x equal to minus y. And this is equal to, remember, we've had the value of y before. If we substitute this value of y here, this will give us minus 1 all over 2, and that will be equal to 1 all over 2. Hence, x will be equal to 1 all over 2. We can see that from this question, we've been able to know the value of, from what we have done, we now know the value of x as 1 all over 2. We know the value of y as what? Minus 1 all over 2. So, why I like this very question is because this question tells you how to derive a formula and also how to find unknown values, like unknown variables, like we have here x, y. There are sometimes they will give an equation that will have x, y, and z. The process is the same. The sequence is the same. Okay. Now let's see how we can arrive. Remember, we now have x value, the value of x. We now have the value of y. But that is not what the intention of the question. The question says we should derive that formula. And so let's see how we can arrive at that formula at this point, having known the value of what? X and y. We say if x is equal to 1 all over 2 and y is equal to minus 1 all over 2, we can now recall that we said earlier that t is equal to 2 pi. Remember from the equation, recall we said t is directly proportional to lx gy, and we further said t is equal to k l raised to power x g raised to power y. So at this point, what you do is to substitute the values of x and y, and this will be t equal to, now k, l, in place of what? X, we're going to have 1 all over 2, and then g raised to power y, that will be 1 all over 2. Well, minus 1 all over 2 represent what? The value of what? Y. And then this is t equal to k, l raised to power 1 all over 2. Of course, you know that this is times. This minus tells us 1 all over indices. Anytime you have a raised to power minus 1, for instance, the minus itself means 1 all over. Why the a will be here and 1 will be on top here. So it means that this is 1 all over g raised to power 1 all over 2. This is equal to k l all over g. You can see that this L has 1 all over 2 and GG has 1 all over 2. So it is L all over G raised to power 1 all over 2. And this is the same as T equal to K, the square root of L all over G, where the square root here represent 1 all over 2. That is indices. So you can see that this formula is similar to the formula that says 2 pi, the square root of L all over G, where our k in this case is what? Constant. The k is the constant. So we have shown, we have proved. So in exams, they can give you a question like this where you may be required to prove that question, to prove a particular formula, or they may ask you to find the value of x and y in a given expression. So the idea is the same, this procedure is the same. You have to apply the methods of dimensional analysis that I have given to you. And again, remember, please don't forget the importance of dimension. That might be the only question you see in your exams. They may ask you, what are the importance of dimensional analysis? We have said you can use it to derive a formula. We have said you can use dimensional analysis to also ensure consistency in unit or confirm the correctness of a unit. These are two basic important you shouldn't forget. So please, I want again to remind you, I've done a video on physical quantities. If you have any problem, any comment that you want to make, please drop it on the comment section, and please don't fail to subscribe and